This is a brief video that's just looking at some of the other ways we can measure absorbance that can take us beyond what's sort of the typical cuvettes and UV vis spectroscopy. So one of the big limits on absorbance spectroscopy or absorption spectroscopy is that the amount of signal you get, your A value, doesn't only depend on concentration, but also depends on path length. So if you're trying to measure something with very small concentrations, if you have a small path length, you're not going to get very much signal to observe, and it might not rise above sort of the noise level or the sort of background level of signal that you get just from your instrument itself. And so a way to measure things that have very small concentrations is to increase that path length, to have a much larger value of B. And so here I'm just mentioning two techniques that are used to do this. One that I use personally in my lab is multipass absorption cells. So that's this here on the top. And we have a nice image of a multipass absorption cell where the laser is actually being shot in here. So this is typically, both of these examples are typically used, or really only used, with lasers because of some of the properties of lasers. You can't use them with typical lamps or broadband light sources that we'll talk about later. But the idea behind a multipass absorption cell is that rather than just put the light through one time, all right, it goes through your sample and that's it, you put mirrors on both sides that are specially designed, and you have the light bounce back and forth, hundreds of times, and then you measure them after it's been able to bounce back and forth. So you can get things, the absorption cell that I have downstairs can go up to 76 meters of path length. You can get things, tens, or even you can get over 100 meters of path length with something like this. So that requires some pretty precise optical tuning and alignment of your laser, but it works. And this is a really commonly used technique to measure things that have very small concentrations or very weak absorbance. A second technique that I have used in the past as a graduate student is something that's known as cavity ringdown spectroscopy. And this has even longer path lengths, but is even finickier to set up. From personal experience, aligning cavity ringdown spectroscopy is a huge pain. Once it works, it's great, but it can be difficult to get it working in the first place. And here you have this similar idea where you have two mirrors, but now these mirrors are really expensive, cost a couple $1,000s a piece, and they're designed to be very highly reflective at the specific wavelength you're trying to measure. So we're talking like something like 99.998% of the light is reflected when the light hits these mirrors. So you use two of these, and two mirrors like this is called a optical cavity. So that's where the cavity of cavity ringdown spectroscopy comes from. And your light will bounce back and forth here, and a small amount of it will leak out over time. And you can measure the amount that leaks out on this side of the detector. Now you can either do this with a pulse laser, where this will sort of naturally ring down or decrease in signal over time, or use a continuous laser, one that puts out light constantly, but have a fast switch that turns it off, and you can watch the light slowly decrease, well, not slowly, it's microseconds, but decrease over time as it leaks out of this optical cavity. If you have something that's present in here that's absorbing the light, though, your light coming onto your detector will decrease much more rapidly because you're just losing the light as it's going back and forth here in your ringdown cavity. And so instead of measuring absorbance, really what you're measuring here is this time it takes for your light to decrease. And your absorption is directly related to that based on R here being the reflectivity of the mirrors. So this gives you a way to measure the absorption without directly measuring the absorption, which can be an advantage for many things. And one of the big things that cavity ringdown spectroscopy does is that it increases your path length even more, right, to sort of kilometer level of path length, whereas your cell is still only like half a meter long or something like that. So these are two other techniques that let us push the boundaries of absorbance spectroscopy using lasers and their properties that are really cool. So just something I thought I'd mention.